Hello everyone, I'm Aman Goel, a PhD student at University of Michigan, working with Professor Karim Sakala. Today I will talk about a new way to automatically verify complex distributed protocols like Paxos, along with provably correct guarantees by using a novel model checking technique. So let's get started.
First, let me summarize what a distributed protocol is. A distributed protocol is a high-level specification of a distributed system, described in a language like TLA+. But simply speaking, a protocol is just like a blueprint of a building. Just like a blueprint is a detailed architectural description of a building, in the same way, a protocol is a blueprint of a distributed system, on top of which different distributed services are built. It does not include a lot of low-level implementation details, but has all necessary information and fundamental details required to implement the distributed system. But first, why do we want to verify such protocols? So that we can avoid outages for cloud computing and other services built on top of these protocols. For example, the content delivery network from Akamai recently faced an outage that was triggered due to a bug in their distributed domain name system. Or to avoid cryptocurrency and security hacks that may cost multi-million dollars, like the very recent DeFi bug in the Compound blockchain, which accidentally gave away $90 million to the users. The bug was due to a single character error in their smart contract, due to using a greater than symbol instead of a greater than equal to in an if condition. Here is the TLA plus representation of a simple protocol called toy consensus, originally written by Ken McMillan. Here, a bunch of voters sent votes to different candidates to elect a leader. And here we have two state variables, vote and leader. And the main thing here to note is that we have a state transition system. As we see at the bottom, we have the initial states and the transition relation formula, with the safety property defined as only a single candidate is chosen as the leader. So distributed protocols are a class of parameterized systems where a bunch of components exchange messages to perform some kind of activity. For example, in the case of toy consensus protocol, a bunch of voters may vote for different candidates, and if the candidate gets enough votes, it is elected as the leader. The main challenge in verifying such protocols is that the domain is infinite. That is, we want to verify for any number of voters and candidates, and this results in the state space being infinite as well. Therefore, automatically verifying them becomes impractical very quickly, with automated reasoning becoming undecidable in several cases. I will present a model checker called IC3PO that can automatically verify such distributed protocols. Given the protocol spec and the safety property, IC3PO performs an automatic analysis and exploration of the state space, and finally outputs whether the protocol is OK or says no, you can fail the property. If the property can fail, IC3PO produces a counterexample trace that shows how to reach the bug from the starting point. If IC3PO says, hey, everything is OK, we also get a proof certificate, that is, an inductor invariant that mathematically explains why the protocol always obeys the property. And both the counterexample traces and proofs can be checked independently to guarantee provable correctness. Here is a summary of the key ingredients of the technique. IC3PO uses finite domain model checking instead of directly verifying the unbounded protocol. And the basic intuition behind this is, as stated recently by Leslie Lamport, the 2013 Turing Award winner in the TLA Plus Google group, quote, "It is rare for an algorithm to be correct for a set of 3 elements and not for a set of 1,000 elements." IC3PO uses the protocol's inherent spatial regularity to perform scalable verification through symmetry-aware clause boosting. We further extended IC3PO to understand temporal regularity in a distributed protocol through range boosting over totally ordered domains, and also to relate these different kinds of regularities with quantification to learn compact quantified clauses. IC3PO now can also use the hierarchy in the specification to scale to complex distributed protocols like Paxos. I will talk about each of these concepts in detail. Let's understand the high-level flow of IC3PO first. Given the unbounded distributed protocol, the property, and an initial size, say 3 voters and 2 candidates, IC3PO first creates a finite instance of the protocol, and it then performs on this finite instance what we call regularity-aware IC3, which extends incremental induction with the knowledge of spatial and temporal regularity and relates them with quantification to perform quantified clause learning. If a counterexample is encountered, we get an execution trace that shows how to reach the bug. Else IC3PO derives a quantified inductive invariant. The next step is to check, have we reached cutoff? That is, have the protocol behaviors converged? If yes, IC3PO outputs the inductive invariant as a quantified proof for the unbounded protocol. Otherwise, IC3PO automatically goes to a higher size to include protocol behaviors missing in the current finite instance. Let's try to understand this with a simple example. Directly performing model checking using SAT and SMT solvers to directly reason about unbounded distributed protocols is hard since the state space is infinite. That is exactly why IC3PO performs model checking on protocol instances of a finite size. By restricting each protocol objects, like voters and candidates here, to a finite set, like 3 voters and 2 candidates. And the benefit we get is that state space is now finite and quite small. Finite domain model checking is always decidable, and we enjoy the benefits of fast SMT reasoning. Next, let's understand different regularities inherent in such distributed protocols. Consider the situation as shown here that says voter B cannot vote to both candidates alpha and beta. Since all voters are symmetrically equivalent, that is, all domain elements in such symmetric domains can be permuted arbitrarily without changing the protocol behavior. Symmetry boosting applies all these permutations in a symmetric domain and learns all of these symmetrically equivalent clauses together. That is, it learns a similar fact with each of the voters, A, B, or C, instead of learning a single clause, and that too without any additional solver reasoning, and encodes these set of symmetrically equivalent clauses as a compact quantified clause. I will not go through how this encoding to a quantified clause works, since we covered this in detail in our earlier work, but here is a summary of it. IC3PO looks at the structure of the clause and the symmetries involved to identify the correct quantifiers that compactly encodes all symmetrically equivalent clauses as a quantified clause. It can be a universal clause with just for all as shown here, or just exists, or a mix of both a for all and exist alternation as required by the clause, or in even more complex forms like for all exist for all by substituting protocol definitions that are already present in the clause. In more involved protocols like Paxos or voting, we have another important dimension, a totally ordered domain called valid here that model the protocol's unbounded but very regular evolution over time. So now there is an unbounded temporal dimension as well. That is, with each vote, there is also an ever-increasing valid number associated. Therefore, there are 3 dimensions of unboundedness, an infinite number of voters and candidates, and an infinite number of valid numbers in the protocol. But similar to symmetric domains, there is indeed a very regular behavior at different valid numbers which we can take advantage of, similar to symmetry boosting. The main challenge that arises is that we cannot simply permute such ordered objects, that is, these valid numbers, since permuting them arbitrarily changes the protocol behavior. Also, there are special elements like the starting valid number 0 here that initializes the valid sequence. We propose a solution along the same lines as symmetry boosting with an important difference. It understands and respects the total order, as well as it checks reachability constraints to limit its boosting to clauses that are permitted by the protocol behaviors. Again, we perform finite model checking as before. For example, let's say with just 4 valid numbers as shown here. And let's say for this finite domain, we come across a situation as shown here. Candidate alpha is chosen in ballot number 1, and voter C is voting for candidate beta in the next ballot number 2. So what the clause we need to learn here is that if alpha is chosen in 1, C cannot vote for beta in ballot number 2. So basically we have two ballot numbers involved here, 1 and 2. We cannot permute them arbitrarily. For example, if we swap 1 and 2 here, the resulting clause is unsafe to learn during reachability. Instead, what we can do is consider all ordered permutations that obey the total order in this finite domain. There are 6 of such ordered permutations here: 01, 02, 03, 12, 13, and 23. And we can ignore all other permutations since they do not obey the total order. Generally speaking, ordered permutations are not guaranteed to be safe to learn in all scenarios. Therefore, we need to explicitly check each ordered permutation through additional SMT queries to make sure we only learn the ones that are permitted by the protocol behaviors. This is different compared to symmetry boosting, where such checks are not needed. And let's say, for example, the solver returns unsat for 3 of these, 1, 2, 1, 3, and 2, 3, while the others are reachable. We can collect these unreachable clauses together and compactly encode them as a quantified clause over an ordered range. For example, here we encode these 3 clauses as: for all x, y in ballot, if 0 is less than x, which is less than y, then if alpha is chosen in x, then voter C cannot vote for beta in y. So this is the main essence of what we call range boosting over totally ordered domains. So this is what IC3PO does to verify the unbounded distributed protocol fully automatically. It performs finite domain model checking along with the concepts of regularity and quantification until convergence is reached. It will auto increase the size if needed, and eventually either produce a counterexample trace that disproves the property or generate a quantified inductor invariant that proves the unbounded distributed protocol as safe. We experimentally evaluated IC3PO against other state-of-the-art automatic verifiers for distributed protocols, where there has been a significant development in recent years. UPDR, also called as PDR for all, performs incremental induction in an unbounded domain. I4 is our previous work that performs finite domain model checking using AVR hardware verifier, followed by generalizing inductive invariance from AVR into an unbounded proof. Both I4 and UPDR only supports universally quantified invariant generation. FOLIC3 performs enumerative search among different quantification prefixes using a separators-based technique while performing incremental induction in an unbounded domain. Swiss is a very recent technique that enumeratively searches for candidate invariants in an optimized and reduced invariant search space. Dist AI is another recent technique that enumeratively searches for candidate invariants using a data-driven learning technique through simulation. Like I4 and UPDR, Dist AI is also limited to inferring only universally quantified invariants. The main difference in IC3PO against these tools is that IC3PO does not search for a particular quantified form or enumeratively searches for different forms. Instead, it uses the protocol structure to boost learning and identify the required form by correlating spatial and temporal regularity with quantification. We used all tools in their default configurations and used the same setup, 1-hour timeout and 32 GB RAM, and included the benchmark suites presented in these different tools, total 40 of them. These include two-phase commit, chord ring, simplified versions of Paxos, etc. On the x-axis, we have the total number of problems solved by each tool, the more the better, and on the y-axis, the runtime, the less the better. UPDR solved 17 problems, I4 solved 19 problems, FOL IC3 solved 24, Swiss solved 23, Dist AI solved 24, while IC3PO solved 39. Overall, IC3PO is much faster compared to the other tools, solving more problems in much less time. It even solved simplified EPR versions of Paxos fully automatically. Here we have a comparison of the size of the inductive invariants compared to human written proofs. That is, the number of clauses in the inductive proof between manual proofs and auto-generated proofs from IC3PO. IC3PO finds compact invariants very much comparable to the human written ones and even smaller in several cases.
Our objective with this work was about automatically proving Lamport's original Paxos specification automatically without any simplification, which still remained unsolved until now. Complex distributed protocols are often designed hierarchically, starting with an abstract specification and stepwise adding more details to finally get the complete specification with all details. For Paxos, we have 5 levels here. Voting is a very high-level specification of Paxos that Lamport wrote without getting distracted with distributed message passing. Then we have simple Paxos and implicit Paxos. And finally, Paxos and multi-Paxos. In order to scale IC3PO to such an involved protocol, we used this hierarchical structure of the protocol specification.
Let's look at the state space size at these levels to get a better idea of these different abstraction levels. Consider the finite instance with, say, 2 values, 3 acceptors, 3 quorums, and 4 ballots. For the voting, the state space is of just 2 to the power 30, that is 30 bits, while for multi-Paxos there are 280 bits for this finite instance. The main point is we can additionally use this hierarchical structure to deal with complexity and achieve high scalability by adding complexity to the verifier in stages, the same way as experts like Lamport design a complex system in stages. Consider a two-level hierarchy, that is a high-level spec and a low-level spec. And let's say the verifier automatically proves the high level and produces an inductive invariant with k strengthening assertions A1 to AK. Let's say if you try to verify the low level spec independently, the verifier does not scale. But if we strengthen the property, that is, pass the strengthening assertions from the inductive proof of the higher level to the lower level, we get a new, much stronger property, which logically can make things very much easier for the verifier, especially for IC3 style model checking. The verifier can then generate the remaining assertions ak+1 till an to get the full inductive proof for the lower level. This we refer as hierarchical strengthening, and we see it as an important structural feature to deal with complexity. We can repeat this strengthening multiple times as well. So starting with voting and without any input strengthening assertions, IC3PO automatically proves voting and generates an inductive proof with two strengthening assertions as shown here, along with their English descriptions. It then passes these two assertions A1 and A2 from voting to simple Paxos to prove the second level and automatically generate 4 more additional assertions A3 to A6. And we can repeat this process. We pass all assertions from previous levels to the next level, that is, passing all A1 to A6, resulting in a strengthened property at this level to get 2 more assertions A7 and A8 that prove implicit Paxos. And finally, passing all above assertions, that is A1 to A8 as input strengthening assertions to Paxos, IC3PO automatically derives 3 additional assertions A9 to A11. Altogether, this inductive proof with 11 assertions provides the first automatically inferred inductor invariant of Lamport's Paxos. Since the crux of proving safety of multi-Paxos is single decree Paxos, the strengthened property with these 11 assertions is already inductive, proving multi-Paxos without any additional assertions needed. Furthermore, this inductor invariant identically matches the human written proof, which is written with enormous manual efforts. This proof can also be checked independently with the TLAPS Proof Manager to further validate its correctness. In summary, we can verify distributed protocols automatically without any undecidability issues, using spatial and temporal regularity to derive compact quantified inductor invariance by using finite domain model checking and incorporating different structural features inherent in distributed protocols. We can also scale automatic verification to large complex hierarchically specified protocols by stepwise adding complexity in stages. We also get provable correctness and guarantees with independently checkable proof certificates and counterexample traces, with a very general approach that finds applications in a variety of different domains. The tool is open source on GitHub, and the paper is available on arXiv. This is the end of my presentation, and please feel free to ask any questions during the talk.